Imagine you're sitting in the cockpit of a fighter jet, traveling at hundreds of miles per hour, when suddenly something goes catastrophically wrong. Engine failure, fire, loss of control, whatever the reason, you have seconds to make a decision that will determine whether you live or die. Your only option is to pull the ejection handle. In an instant, explosive charges detonate beneath your seat, and you're blasted upward with a force so violent it feels like being hit by a truck. Within 0.2 of a second, you've been launched hundreds of feet into the air, clear of the aircraft that was about to kill you. But here's the paradox. The human spine is fragile. A bad fall from a ladder can fracture vertebrae. A car accident at moderate speed can cause permanent spinal damage. Yet somehow, pilots routinely survive ejections that subject their bodies to forces 15 to 20 times the force of gravity, sometimes even more. So, how is this possible? How does an ejection seat launch a human being with enough force to clear a speeding aircraft, often in fractions of a second, without snapping their spine like a twig? The answer lies in decades of engineering research, careful understanding of human biomechanics, and a design philosophy that treats the pilot's body not as a passenger, but as an integral part of a precisely controlled system. Ejection seats aren't just chairs with rockets attached. They're sophisticated life support systems engineered to distribute force, control acceleration, and protect the pilot's body from the very violence that's saving their life. Every element, from the seat position to the timing of the rocket burn, has been calculated to push the human body to its absolute limits without crossing the line into catastrophic injury. To understand how this works, we need to break down what actually happens during those critical 0.2 of a second and why the human body can survive forces that seem impossible. When a pilot pulls the ejection handle, a sequence of events begins that happens faster than conscious thought. The first thing that occurs, even before the seat moves, is the canopy is jettisoned or shattered. Some systems use explosive cords embedded in the canopy glass to fragment it, while others mechanically blow the entire canopy away from the aircraft. This has to happen first because launching a pilot through solid glass would be fatal. Once the canopy is clear, typically within 0.1 seconds, the seat's primary rocket motor ignites. This is not a gradual push, it's a violent, instantaneous acceleration. The seat, with the pilot strapped in, is propelled upward by a solid fuel rocket or a ballistic charge that generates thousands of pounds of thrust. Within the next 0.1 to 0.2 seconds, the pilot and seat are traveling fast enough to clear the aircraft's tail, which at high speeds could be moving toward them at hundreds of miles per hour. This entire launch sequence, from handle pull to separation from the aircraft, happens in less time than it takes to blink. The force involved in this process is measured in Gs, or multiples of gravitational acceleration. During a typical ejection, pilots experience between 12 and 20 Gs, sometimes spiking even higher depending on the aircraft's speed and altitude. To put that in perspective, 1 G is what you feel standing on Earth. Fighter pilots routinely experience 9 Gs during high-performance maneuvers and are trained to handle it. But ejection forces can be nearly double that, applied not over several seconds, but in a fraction of one. At 20 Gs, a pilot who weighs 180 pounds effectively weighs 3,600 pounds for that brief instant. Every organ, every bone, every vertebra in the spine is subjected to forces far beyond what the body normally encounters. So, why doesn't the spine shatter? The key is in how the force is applied. The human spine can withstand surprisingly high loads if the force is distributed correctly and applied along the right axis. The spine is strongest when loaded vertically, from head to pelvis, along its natural column. This is exactly how ejection seats are designed to apply force. The pilot sits in an upright position with their back pressed firmly against the seat. When the rocket fires, the force pushes upward through the seat pan, transferring load through the pelvis and up through the spine. The seat back provides critical support, preventing the spine from flexing or twisting during acceleration. This keeps the vertebrae aligned and distributes the force evenly across the entire spinal column rather than concentrating it at any single point. If the pilot were leaning forward, slouched, or twisted when ejection occurred, the risk of spinal fracture would increase dramatically. Modern ejection seats also include features specifically designed to minimize spinal injury. One of the most important is the seat's stroke or telescoping mechanism. As the rocket fires and the seat accelerates upward, the seat itself is designed to compress or stroke downward slightly relative to the pilot. This controlled movement acts like a shock absorber, spreading the peak force over a longer period of time. Instead of the full force hitting the pilot's body in an instant, the stroke mechanism extends the acceleration phase by a few milliseconds, reducing the peak G load. This might not sound like much, but in the world of ejection dynamics, milliseconds matter. The difference between 18 Gs and 22 Gs can be the difference between walking away and spending months in recovery. Another critical factor is pilot preparation. Before ejection, pilots are trained to assume a specific body position. They pull their arms and legs in close to their body, tuck their chin to their chest, and press their back firmly against the seat. This position serves multiple purposes. Tucking the chin prevents neck hyperextension, which could cause whiplash or cervical spine injury. Pulling in the limbs prevents flailing, which could result in broken arms or legs as the body is subjected to extreme forces and high-speed airflow. Pressing against the seat back ensures proper spinal alignment. In modern ejection seats, leg restraints automatically retract when the handle is pulled, forcibly pulling the pilot's legs back against the seat to prevent them from being struck by the instrument panel or damaged by wind blast. This automation is crucial because in an emergency, pilots may not have time to consciously assume the correct position. The ejection seat's rocket motor is also carefully calibrated. It doesn't burn at maximum thrust for the entire ejection sequence. Instead, it's designed to produce just enough force to clear the aircraft as quickly as possible while staying within the human body's tolerance limits. Engineers have spent decades testing and refining the thrust profiles of these rockets, using crash test dummies equipped with sensors that measure spinal compression, head acceleration, and organ displacement. The goal is to find the sweet spot where ejection is fast enough to save lives, but controlled enough to prevent injury. In some advanced systems, the rocket thrust is variable, adjusting based on the aircraft's speed and altitude to optimize the ejection trajectory while minimizing G-forces. Despite all these precautions, ejections are not without risk. Spinal compression injuries do occur, even with the best engineering. Studies have shown that a significant percentage of pilots who eject experience some degree of spinal compression, often resulting in a permanent loss of height, sometimes as much as an inch or more. This happens because the forces involved, even when properly distributed, can compress the cartilage discs between vertebrae. In severe cases, pilots suffer fractured vertebrae, though modern seats have reduced this risk dramatically compared to earlier designs. The trade-off is clear. A compressed spine or a fractured vertebra is painful and requires treatment, but it's survivable. The alternative, staying with a doomed aircraft, is not. There's also the issue of what happens after the seat clears the aircraft. Once the pilot is airborne, the seat's job isn't done. A drogue chute deploys to stabilize the seat and slow its descent, followed by the main parachute, which is either deployed automatically or manually by the pilot depending on altitude. Throughout this sequence, the seat continues to protect the pilot. The seat pan and back provide a stable platform that prevents tumbling, and in some systems, the seat separates from the pilot only after the parachute has fully deployed, ensuring the pilot doesn't enter freefall unexpectedly. All of this is controlled by sequencers and timers built into the seat, designed to function even if the pilot is unconscious or incapacitated. Ejection seat technology has come a long way since its early days. The first ejection seats, developed during World War II, were crude by modern standards. They used explosive charges or compressed air to launch the pilot with little consideration for spinal protection. Injury rates were high, and many pilots who survived ejection suffered permanent damage. Over the decades, advances in materials, biomechanics, and rocket propulsion have transformed ejection seats into highly sophisticated systems. Modern seats like the Martin Baker Mark 16 and the ACES-2 used in American fighters incorporate computer-controlled sequencing, variable thrust rockets, and advanced restraint systems that drastically reduce injury rates. These seats can save pilots at 0 altitude and 0 airspeed, meaning they can function even if the aircraft is sitting still on the runway, a feat that would have been impossible with earlier technology. The bottom line is this: ejection seats don't prevent spinal injury by eliminating the forces involved. They prevent catastrophic injury by controlling how those forces are applied. The spine is kept aligned, the force is distributed evenly, the acceleration is spread over the longest practical time frame, and the pilot's body is positioned to withstand the load. It's a balancing act between speed and safety, between the need to escape a lethal situation and the need to keep the pilot alive and functional afterward. The fact that pilots routinely walk away from ejections that subject them to forces equivalent to a severe car crash is a testament to the precision of this engineering. So the next time you see footage of a pilot ejecting from a fighter jet, understand that what looks like a simple explosive launch is actually the result of decades of research into human limits and survival. That pilot's spine isn't breaking because every element of the seat, from the rocket's thrust curve to the position of the leg restraints, has been designed to push the human body to the edge of what it can endure without crossing into permanent damage. It's violent, it's dangerous, and it's not without risk, but it works. And in the split second when everything goes wrong at 30,000 feet, that 0.2-second escape is the difference between life and death. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution.